Alright, hey, let's get started with this video right here. Whoa, almost fell up. So, trying to figure out how this little camera works, but we're going to switch right now to the thing you're used to seeing. I'll talk to you in a little while. There we go. The piece that you're normally used to seeing is a lovely photograph and the topic. Oh, I'm so sorry. So, sorry, we're booked for supper. Sometimes we reach the limit. This is at the can't see it, but it's at the Lady and Sons in Savannah, Georgia, and this was about 3 o'clock in the afternoon. No more room for supper. So, analytic limits. So we've been doing limits with numerically, graphically. Now we're going to use our math piece and work from there. So what we're looking for is we're going to try to find functions that agree at all but one point. Sounds highfalutin, but that'll be okay in a little bit. Basically, if we've got two functions that are the same except for all the x's except for possibly one particular value, and we know the limit of one of the functions is L, and we can make the jump that the other limit has a function of L. Okay, hang on to that thought. We're looking for two functions that are essentially the same except for they're both defined. Got a couple of techniques. First one is called cancellation. Cancellation works like this. Well, we cancel. If I were right away just to try to pop in x equals 3 right here, x equals -3 on the top, I get -3 squared plus 5 times -3 plus 6 squared, and on the bottom I get -3 plus 3, which ends up, the bottom comes out to be 0. The top I end up with 9 minus 15, which is -6 plus 6, which is also 0. And so I end up with 0 over 0, and 0 over 0 is what we refer to as an indeterminate form. Okay, the reason we call it indeterminate form, well, because anything divided by itself is 1. So it's 0 to 0 divided by 0, 1. Or we use the rule where we can't divide by 0. Tricky, huh? So, indeterminate form, we get 0 over 0. What that means in calculus, it means that we've got more work. When we get 0 over 0, we end up having to do some more work. I'm going to eliminate all this stuff to make our life a little clearer. You wrote it down, so if you didn't, pause, rewind, you know how it works. Alright, so, okay, there it is. So, I can factor x squared plus 5x plus 6. I can factor it into x plus 3 times x plus 2. If I have that over x plus 3, which is what we have the denominator anyway, I can now cancel the x plus 3's, because x plus 3 divided by x plus 3 is 1. Can always divide by 1. So I'm left with a function that essentially is the same function as I started with, except my function that I have now is defined when x equals -3. The original one I get 0 over 0. This new function that's essentially equivalent is divisible. So now I can plug in -3 plus 2, I think, is -1. So the limit of this function is -1, the limit of this function is -1, the limit of everything is -1. So cancellation involves factoring and canceling. We'll try a couple more, perhaps one that's a little more difficult. All right, remember x cubed minus 1, okay, divided by x minus 1. I forget what that canceled in, what that factored into, so I'm going to quick do the thing. I think it's x squared plus x plus something, but x cubed minus 0x squared. All right, let's go plus 0x squared plus 0x minus 1 factors x squared leaves me x cubed minus 1x squared. Bring it down. Remember, subtract the negative makes it a positive, plus 0x. Alas, I have no more room. Oh, there, I do have some more room. Subtract, so then so this I need to go with x times. So x squared, so plus x. X times 1 minus x squared. Subtract, I'm left with 1x minus 1, which is going to go into there one time. So, we have a formula for that, we'll figure it out. So that's the same as the limit as x approaches 1. Forgot to mention, if you plug 1 in here, 1 minus 1 is 0, 0 minus 1 is 0. 0 over 0 means we have more work to do. The more work, factoring it. This is factors, because that's really what division is finding the factors. x squared plus x minus 1. That's the same as x cubed minus 1. On the bottom we have x minus 1. Cancel away. And we're left with an equivalent function, only this function, weird m, this function is defined when x equals 1. Right? So when x is 1, I get 1 squared plus 1 minus 1. Plus 1 is 2, 2 minus 1 is 1, so this function has a value of 1. The limit of this function is 1, the limit of my equivalent function is 1, they're the same. So we're just trying to find that equivalent function. Okay? I think I'll leave this one for you to do. We can real quick check in. 9 minus 3 minus 6 more is 0, negative 3 plus 3 is 0, 0 over 0, indeterminate form. Means more work to be done. So you can try that one. I'm not going to put it on in 30 seconds, and don't sit there and wait. Actually do this one, and we'll check in with it. We'll check in with it tomorrow. All right, we're moving on to technique number 2 for today. It's called rationalization. It doesn't mean we're trying to convince ourselves that we can do this. It means we actually are trying to get rid of the square rooty thing. Okay. What we're going to do is we're going to use the conjugate. And you've heard the word before, hopefully, but conjugates are things like x plus 3 and x minus 3. Things like 2x plus 5 and 2x minus 5. The deal is we left the terms the same, we just changed the sign. So one's plus, one's minus, one's plus, one's minus. So the conjugate of this thing here is the square root of x plus 1 plus 1. I'm going to multiply, but I can't just multiply the top by that. I've got to multiply top and bottom by that same conjugate. Okay, I'm going to get rid of the stuff down the bottom quickly. Basically what I've done is I've multiplied by 1 and multiplied this thing by 1. Okay, that's 1. Why the conjugate? That's probably what you're asking. Well, let's see what happens. When I multiply the first times the first, the square root of x plus 1 times the square root of x plus 1, that's x plus 1. When I multiply the inside, I get negative square root of x plus 1. When I multiply the outside, I get positive square root of x plus 1. So my square roots are gone. Bingo, gone. And then I do the last piece, and it's positive 1 times negative 1. That's that. Down bottom, we're just going to leave this just like it is. Okay? So, simplifying just a touch further, x plus 1 minus 1 is x over x times the square root of x plus 1 plus 1. Lo and behold, I got an x top and bottom. Let's cancel in a fancy colored pen. That is very fancy. X, x. Remember, I'm left with a 1 here. I can't turn a fraction into a non-fraction just because I feel like it. So what I've done is I've found an equivalent function, because all I did was multiply this function by 1. That's the same as that function. But now when I plug 0 in, I get a value. 1 over the square root of 0 plus 1 plus 1. 0 plus 1 is 1. Square root of 1 is 1. 1 plus 1 is 2. 1/2. Lo and behold, rationalization has found us a limit. Okay? Using the conjugate. We'll get some more practice with that as we move forward. Right. What else we got? Oh, we've got some special trig limits. That's what it says right there. Some special trig limits. So there they are. The limit as x approaches 0 of the sine x over x is 1. For right now, you're going to have to take my word for it. The limit as x approaches 0 of 1 minus the cosine of x over x equals 0. This checking sine of x, sine of 0 is 0, 0 over 0. In this case, we're going to say it's 1. And then the other way, 1 minus the cosine of 0, which is 1. 1 minus 1 is 0 over 0. Okay, in this case, it's 0. Some special ones, we're going to write those down. We're going to put a box around them. We might put, I don't know, some other decorative feature around them so that we remember. Ooh, let's use the magic smiley face. No, we'll use the star pen. Okay, we want to write those down. We'll use them on the very next slide. There they are. So we're going to use those to figure out what the limit as x approaches 0 of tan x over x is. What's tangent? sine of x over the cosine of x. And all of that is over x. Sine x for cosine x over x. So remember, this little x is like x over 1. So I'm going to rewrite this as sine x over cosine x times 1 over x. Division, invert, and multiply. I'm going to rearrange that so it's the sine of x over x times 1 over the cosine of x, which had a bigger screen. Okay, all the time still, we're looking to take the limit as x approaches 0. But we know what the limit as x approaches 0 of sine x over x is. Put stars around it. There it is, it's 1. So this thing's 1. And cosine of 0 is 1. 1 over 1 is 1. So this is 1 times 1, which is 1. Ta-da! Great. Now, this one on the bottom. This is quick. This will be fast. All right. So, I don't know what the sine of 4x over x is. I can rewrite that as the limit as x approaches 0 of the sine of 4x over 4x. Can I do that? No, I can't just randomly divide by 4, right? I can't just randomly divide by 4 unless, at the same time, I multiply by 4. Multiply by 4, divide by 4. Essentially, I've just multiplied by 1. No big deal. Okay? Now, this is where it's going to get crazy. 4, limit, as x approaches 0, of the sine of y over y. Why? Because y equals 4x. I just decided that. So the limit is as, oops, think that y approaches 0. As y approaches 0 of the sine of y over y, it's 1. All this is 1. Put stars around it, remember? I'm not going to go back. So that's 1. All this garbage here. 4 times 1, 41. It's 4. Okay? See how special those are? How much they help us figure things out? Great. Alright, last thing. I'm just going to put this on the screen. The squeeze theorem. I'll read it. If the h of x is less than the f of x, which is less than the g of x for all x, except maybe c, and the limit as x approaches c of the h of x is equal to the limit as x approaches c of the g of x, which is equal to L, then the limit as x approaches c of the f of x is equal to L. We, tomorrow, in class, will do the squeeze theorem, interpretive, am I spelling this right? Interpretive dance. It's the only real way to understand the squeeze theorem is to dance it out. So we look forward to doing that tomorrow. We'll talk further about the squeeze theorem and interpretive dance. I think that's all there is. Should we go back, see if I'm still hanging around over there? Let's go back to it. So we've learned a lot. We've learned the interpretive dance. We've learned I can flip sideways. Oh, there I am. We've learned We've learned that we're going to do interpretive dance. Oh, scary looking. Going back to this. We can like me upside down there. Okay. So we've learned about interpretive dance. We've learned the squeeze theorem. We've learned about cancellation. We've learned about rationalization. If you have questions, please ask tomorrow. Thanks for watching. Hope you learned something. Bye.